Very good morning to one and all, and I welcome you all in the next lecture of heat transfer. Whether my voice is audible and can you see my presentation? Please let me know in the chat box. Thank you. Great. So we'll start now. In the last lecture, we have discussed the overall heat transfer coefficient. Okay, that is nothing but capital U. So when we required this capital U or overall heat transfer coefficient, so for that purpose, self-explanatory diagram I have provided to you. So that is nothing but what the metal wall is there, and from one side of a wall, the hot fluid is flowing, or any kind of a fluid is there. Okay, so here you can consider water or air, no problem. So consider that the hot water is flowing on one side, and another side the cold fluid is flowing. So in that case, the heat will transfer across the metal, okay, or across the metal wall, or across the any material wall. Okay, so in that case, there is presence of a convection and conduction mode of a heat transfer. So one can say that whenever the heat is transforming from a liquid to the material, okay, or from fluid to the surface, then that heat transfer we need to consider as the convection mode of a heat transfer. And whenever, in a similar fashion, whenever the heat is transforming from surface to liquid, okay, from surface to liquid, in that case also the mode of heat transfer is convection heat transfer. Convection heat transfer. So in that case, this overall heat transfer coefficient is useful to determine the heat transfer rate across the wall surface, okay, or across that particular entire system. Okay, so in that case, we have seen that first of all, we have applied the Newton's law of cooling for the heat transfer from hot fluid to the surface of a wall on that particular hot fluid side, and we get the equation. Okay, and that equation we have converted into a temperature difference. Once again, the heat will transfer through the within the metal wall. Okay, within that particular thickness of a wall. So within the material, the heat transfer will be considered as a conduction mode of heat transfer. So in that case, we have to apply the Fourier's law. Okay, then further, the heat will transfer from wall surface to the cold fluid, and that will be the convection mode of heat transfer. In that case also, we have to apply the Newton's law of cooling, and we have applied that, and we have converted that equation into a temperature difference. Then we have added this all the three equation number 2, 4, 6, addition in a such a manner that the temperature should be added on one side, and or the left side should be added on a left side, and the right side should be added on the right side. Okay, so then we have just done some rearrangement of variables. Okay, so we will get the equation in the form of a T suffix hf minus T suffix f, where this T suffix hf and T suffix cf are the extreme temperatures of the system, or we can say that extreme temperatures for that particular diagram. And once we converted that equation into a heat transfer rate, okay, so that then we will get this particular equation. Now, in this particular case, the 1 upon whole divided by this particular bracket will be equal to U. Okay, will be equal to U. U is nothing but overall heat transfer coefficient. Okay, and will U will be given as U is equal to 1 upon whole divided by 1 upon H suffix HF plus L divided by K plus 1 divided by H suffix CF. Okay, so that we have discussed in the last lecture. Now, we will take one problem on this particular point, and then we will move ahead to the next point. Okay, so write down the problem. Problem number 5 on a wall, composite wall. Problem number 5. A mild steel. Write down the problem, everyone. A mild steel tank. A mild steel tank. A mild steel tank of wall mild steel tank of wall 12 mm, mild steel tank of wall 12 mm, mild steel of wall wall thickness. Write down here wall thickness. Okay, wall thickness. Mild steel of tank of wall thickness 12 mm contains water at 95 degrees Celsius. Contains water at 95 degrees Celsius. Full stop. Full stop. The thermal conductivity of mild steel is 50 watt per meter degree Celsius. The thermal conductivity of mild steel is 50 watt per meter degree Celsius, and the heat transfer coefficient for inside and outside the tank, and the heat transfer coefficient for inside and outside the tank are 2850 and 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 10 2850 and 10 watt per meter square degree Celsius respectively. Watt per meter square degree Celsius respectively. If 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 the atmospheric temperature is 15 degrees Celsius, if the atmospheric temperature is 15 degrees Celsius, calculate the rate of heat loss, the rate of heat loss per meter square of the tank surface area. The rate of heat loss per meter square of the tank surface area. And the second one, the temperature of the outside surface, of the tank, temperature of the outside surface of the tank. Okay, so that too we need to calculate. So in a rough manner, what is given data? Thickness of a wall is provided 12 mm. Okay, and that particular steel tank contains a water which is having a temperature of a 95 degrees Celsius. Okay, then thermal conductivity of mild steel tank is provided. Okay, and it is equal to 50 watt per meter degree Celsius. Then heat transfer coefficient. Okay, so heat transfer coefficient for the heat transfer for mode of a convection heat transfer, which is the constant heat transfer coefficient, or convective heat transfer coefficient is the constant one, and that constant is provided. Okay, for the inside, that is nothing but water is present inside the tank. So hot water to tank wall. Okay, so heat is transforming by convection mode of heat transfer. In that case, we require the convective heat transfer coefficient. Also, from the wall to the external atmosphere. Okay, external atmosphere, that is nothing but free air available outside the tank, and that heat transfer from the outside surface to the atmosphere will be considered as a convection mode of heat transfer. And in that case also we require the constant of proportionality, that is the convective heat transfer coefficient. So that two constants are provided. Okay, that two constants are provided, and they are equal to 2850 and 10 watt per meter square degree Celsius. And the outside atmospheric temperature is provided. Okay, outside atmospheric temperature is provided. So we can draw this diagram easily, that we have to show the wall thickness of tank. Okay, so tank wall, this is the tank wall. Okay, and inside that particular tank wall water is present. Inside that particular tank wall water is present, and this water is having the temperature of 95 degrees Celsius. That will be, you can nominate it as a T suffix HF. Okay, that is the hot fluid temperature, and it is equal to 95 degrees Celsius. Okay, now the wall is having the thickness of L is equal to 12 mm. Outside the wall or outside the tank there is atmosphere, and which is having the temperature of a 15 degrees Celsius. So you can nominate this temperature as T suffix CF. Okay, so that is equal to cold fluid temperature. Cold fluid temperature. Okay, and the heat will transfer from the inside fluid to the outside fluid of that particular tank. Inside fluid of the tank to the outside fluid of the tank. So this is the problem, and we have to determine the rate of heat loss from the water to the external environment. From the water to the external environment. And second thing, we have to find out the outside surface temperature of the tank. That is nothing but T2. We have to find out the outside temperature of the tank. That is nothing but T2. Okay. So given data, you can write L is equal to 12 mm. That is the thickness of a wall, and it is equal to 12 mm, which is equal to 0.012 meter. 0.012 meter. Write down everyone. Then T suffix HF, T suffix HF, T suffix HF is equal to, T suffix HF is equal to 95 degrees Celsius. That is the hot fluid temperature. And T suffix CF, T suffix CF is equal to 15 degrees Celsius. Is equal to 15 degrees Celsius. Then thermal conductivity of wall is provided, which will be considered as a K. K is equal to 50 watt per meter degree Celsius. 50 watt per meter degree Celsius. Also remember the difference between the units. Okay. So watt per meter degree Celsius is the unit of a thermal conductivity, whereas watt per meter square degree Celsius is the unit of a heat transfer coefficient. Okay, these two are the constants. So K is equal to thermal conductivity and thermal conductivity of a wall, and it is equal to 50 watt per meter degree Celsius. Whereas the hot fluid heat transfer coefficient, that is the water heat transfer coefficient, we can nominate it as a H suffix HF. H suffix HF. It will be equal to 2850 watt per meter square degree Celsius. Okay. Then the cold fluid heat transfer coefficient, that is H suffix CF, H suffix CF will be equal to 10 watt per meter square degree Celsius. 10 watt per meter square degree Celsius. And we have to determine Q by A, that is the heat transfer rate per unit area. And second one is T2, that is the outside temperature of a wall, outside surface temperature of a wall. Okay, so that two things we have to determine. Draw the diagram, write down the given data appropriately. So on the basis of problem, we have to imagine the diagram, and once the diagram once we draw the diagram, at that time it will be easy to solve the problem. Okay, we have to apply the formulas according to the diagram, and we have to solve the problem. Okay, so diagram is important, so that will provide you the correct solution or correct imagination to solve the problem. Okay, So have you drawn the diagram? Okay, then let's start with the first solution, rate of heat loss per meter square. Now this is the concept of overall heat transfer coefficient. Okay, this is the concept of overall heat transfer coefficient. Just we have discussed the overall heat transfer coefficient. So in case of a overall heat transfer coefficient case, we have to write the equation for a rate of heat transfer as Q is equal to U, capital U multiply by A multiply by into bracket T suffix HF minus T suffix CF, where whereas this U is the overall heat transfer coefficient, is the area available for the heat transfer, and multiply by T suffix HF is the temperature of a hot fluid, and T suffix CF is the temperature of a cold fluid. Okay, getting everyone? Now, in this case, T suffix HF and T suffix CF are the known quantities. Okay, and U we can transfer on this side, and because we have to find out the rate of heat loss per meter square. So that is nothing but Q by A. So that we can transfer this A on this side, and only unknown is U. Okay, only unknown is U, and for that reason we have to consider the formula for U, that is the overall heat transfer coefficient. Okay, now we have transfer A from the left side, so it will be Q by A is equal to U multiply by into bracket T suffix HF minus T suffix CF. Okay, write down everyone. Q by A is equal to U multiply by T suffix HF minus T suffix CF. Okay, now we have to determine the U value. Okay, and for that reason we require the U formula for overall heat transfer coefficient. Or now U is equal to 1 upon 1 upon whole divide 1 divided 1 whole divided by into bracket 1 divided by H suffix HF plus L divided by K plus 1 divided by H suffix CF. By using this formula, you can easily determine the overall heat transfer coefficient. Okay. Now we have to put up the values of HF, H suffix HF, L, K, and H suffix CF in the formula of U, and we can determine the U value. Okay. Do calculation everyone, and please let me know the U value in the chat box. Please let me know the value of U in the chat box. Use calculator, calculate it, and you can answer in the chat box. Okay, directly Q by A answer. What is U? U, overall heat transfer coefficient. U is equal to 9.94. Great. Right. 9.94. U is equal to 9.94, and its unit is watt per meter square degree Celsius. Okay, its unit is watt per meter square degree Celsius. Once you will get the U value, so once you will get the U value, just put up that U value in this particular equation. Q by A is equal to U multiplied by T suffix HF minus T suffix CS. So Q by A, we know that the heat flux, heat transfer rate per unit area is nothing but heat flux. So we can say that Q by A is equal to small q is equal to U multiplied by T suffix HF minus T suffix CF. Okay, just put up the values of and find out 9.94 multiplied by into bracket, what is T suffix HF? 95 minus 15. Okay, and which will be equal to what you are getting. Calculate it. So someone is getting 795.2, 0.3. So my answer is 795.2. Okay, and its unit will be watt per meter square. Okay, and its unit will be watt per meter square. Okay, getting everyone how to find out the heat transfer rate in case of overall heat transfer coefficient. Now, second thing, we have to determine the temperature of the outside surface of the tank. Okay, temperature of the outside surface of the tank. So we have determined the Q by A by using the same Q by A, because the overall heat transfer rate across the wall is same one. Okay, so we can say that the temperature of outside surface of a tank we can determine by using the Newton's law of cooling. This equation we have used in our derivation, Newton's law of cooling. We know that the heat transfer from the outside surface of wall to the outside environment, okay, will be considered as a convection heat transfer. So in that case, we have to use the Newton's law of cooling. So we know that Q is equal to H suffix Cf multiplied by area multiplied by T2 minus T suffix Cf. Okay, T2 minus T suffix Cf. Okay, so this is the equation for the heat transfer from the outside surface of a tank to the external environment, where this H suffix Cf is the convective heat transfer coefficient of a cold fluid. Convective heat transfer coefficient of a cold fluid. Just we have to rearrange this equation in the form of a Q by A, because we know the value of a Q by A. So we have converted this equation in the form of a Q by A by transforming area from the right side to the left side. So Q by A is equal to small q will be equal to H suffix Cf multiplied by T2 minus T suffix Cf. T2 minus T suffix Cf. Just put up the values of H suffix Cf, T suffix Cf and Q by A in this equation and determine the value of T2. Determine the value of T2. Okay. Determine the value of T2 and let me know the value of T2. H suffix Cf value is 10, and into bracket I will write T suffix 2 minus T suffix Cf is 15. Okay. Insert multiplication symbol. Okay. Have you get the value of T2? Determine T2 now. Okay, someone getting 94.52. Whether this is right answer or wrong, please put up your also. T2 is equal to. Okay, same answer. Nihal and Yash are getting same answer. So it is equal to 94.52. Okay, and it will be unit will be degree Celsius. Okay, unit will be degree Celsius. Okay, T2 is equal to 94.52 degrees Celsius. So that will be our final answer. T2 is equal to 94.52 degrees Celsius. Getting everyone how to solve the problem on overall heat transfer coefficient, and when we have to use the overall heat transfer coefficient, that is also important thing. Okay. Now the next point is we have covered all the points related to wall. Okay, or we can say that the Cartesian coordinate system. Okay. Now the next important point is general heat conduction equation in a cylindrical coordinates. General heat conduction equation in a cylindrical coordinates. Okay. Now why we required the another coordinate system? Because in the objects are changes. If you consider the rectangular geometry, so in case of a rectangular geometry, uh, every point in that rectangular geometry can be measured by using the xyz direction. That is nothing but the Cartesian coordinate system. But in case of pipe geometry or the rod geometry or a cylindrical type of a geometry, okay, cylinder means what? The cross section is a circular one and it is having height. Okay, that is nothing but a cylinder. So in that case, we need to apply the cylindrical coordinate system. So in a cylindrical coordinate system, we cannot, or in a cylindrical geometry, we cannot measure all the points by using xyz direction, or it will be very we can say that very fumble one, or it will not be a simple measurement for the cylindrical geometry to apply the Cartesian coordinate system. So in that case, we have to consider the cylindrical geometry. Okay. So while dealing with the problems of a conduction of heat through system having cylindrical geometries, okay, which are the cylindrical geometries? Rods, pipes, etc. This will be considered as a cylindrical geometries, and it is convenient to use the cylindrical coordinates in case of a cylindrical geometry. Okay, if you want to determine the conduction in a cylindrical geometry, you have to apply the cylindrical coordinate system. Okay. Now, let us understand what is meant by cylindrical coordinate system. Okay. So consider this is the hollow cylinder. Okay. Consider this is the hollow cylinder. So hollow cylinder is having the two radius. Okay. One is the internal radius and one is the external radius. Okay. So here in this particular diagram, internal radius is shown as R2 and external radius is shown as R1. Okay. So if you take the front view, then we know that in graphics we have discussed how to take the front view of a cylindrical geometries. So in case of a cylindrical geometries, the front view will be a rectangular one. Okay. And the top view will be a square one, the circular one. Okay. The top view will be the circular one. So in case of a front view, you will see the height of that particular cylinder. And in case of a top view, we will see the two radius of, or the cross section area of that particular cylinder. Okay. Now imagine what is meant by cylinder. Okay. From this particular diagram. Now, how to measure the coordinates in a cylindrical geometry? How to measure the coordinates in the cylindrical geometry? Which are the coordinate system? Okay. So here, the coordinates we measure by using r, theta, and z. Okay. R, theta, and z. This is the coordinate system we are going to apply for the cylindrical geometry. R, theta, and z. Okay. Where z is nothing but what? Z is nothing but height from the surface. Consider that this is the P point we have considered in a cylinder. Okay. And we have to measure the coordinates of this particular P points. So how one can measure the coordinates of this particular P point? So in that case, we have to take the help of a general coordinate system or a Cartesian coordinate system. Okay. First of all, this is the z-axis or y-axis. We can say that, z-axis. This is the z-axis. This is the x-axis, and this is the y-axis. Okay. So this is our general coordinate system. Now, the z coordinate can be measured vertically. Okay. The height of that particular point from the base. okay, the height of particular point from the base, okay, so that will give you a z coordinate, okay, height, this is the height. So this is the base is the xy plane, base is the xy plane, okay. From the base, how much or how much distance this particular p point is placed vertically, so that will be a z coordinate, okay, that will be the z coordinate. Now, what is meant by r coordinate? R coordinate is the distance from the center line. Okay, R coordinate is the distance from the center line. Okay, so this is the center line or the axis line for the cylinder. Okay, from this axis point, at what distance this particular P point is placed, that is nothing but R coordinate. Okay, that is nothing but R coordinate, or the radius of that particular point from the center in a cylinder. Okay, so center line will be considered as a axis of that particular cylinder. Okay, so R coordinate is the distance from the center. Now the middle coordinate is nothing but a theta or phi. You can consider phi or theta here. Now, how one can measure the theta or phi coordinate in this particular cylindrical coordinate system? So, theta or phi, once we draw the straight line from the axis to that particular point, it will provide you r distance. Okay, it will provide you r distance. Now, the angle made by this particular line with the x-axis, okay, with the x-axis, angle made by this particular line, once you draw the straight line which is connecting that point and the central axis of the cylinder, if you draw this particular line, this line made some angle with the x-axis, okay, so that angle will be considered as a theta or phi. Okay, so in this manner we can locate any point in a cylindrical coordinate system about the cylindrical geometry, so P point can be measured by using r theta z or r phi z. Okay, so you can consider the phi also, r phi z. Okay, so the coordinates for the cylindrical geometry is r phi z. Okay, so in a simple diagram you can draw this diagram. Okay, so we want to locate the a point, in a cylindrical coordinate system. So we have drawn simply our general coordinate system x, y, z. Okay, and we have to locate the a point. So distance from the center point to that particular, or center line to that particular point, will be r. Okay, the angle made by the line joining r with line joining the point with the center and the x-axis will be considered as a phi, and the height from the base plane will be considered as a z. Okay, will be considered as a z. So the coordinates of a point in a cylindrical coordinate system are r, phi, and z. Coordinates of a point in a cylindrical coordinate system are r, phi, z. Getting everyone what is meant by cylindrical coordinate system and which are the coordinates used for locating any point in a cylindrical coordinate system? Getting everyone? Is there any question, any doubt? So please draw this diagram. You can draw the simple cylinder, okay, by showing the front view and top view, and draw the axis, draw the diagram which is showing the coordinates of cylindrical coordinate system. Okay, so first of all, draw this particular simple diagram of a cylinder. Is there any question, any doubt? Whether you understood what is meant by cylindrical coordinate system and how to locate the coordinates or the points in a cylinder? Okay, draw this diagram, simple one. Freehand drawing is required. From this diagram, we will understood that there are two radius for the cylinder, hollow cylinder. Okay, this is the hollow cylinder. Okay, and the height of the cylinder. Okay, height of the cylinder. Okay, in front view and in top view, we can understand the radius or the circular geometry or the cross-sectional area of that particular hollow cylinder geometry. Okay, so next, don't draw this diagram, draw this one, okay, which is showing the axis formation of a cylinder, cylindrical geometry, which is showing the axis formation of cylindrical geometry. Okay, Z is the height from the base. So if you are considering that the cylindrical cylinder is placed on a plane surface, so if you want to locate the any point on the cylinder and what is the height of that particular point from the base, that will be the Z coordinate. Okay, then the distance from the center line, that will be the R coordinate, and if you join this particular line, if you draw this particular line on a base surface, that is the uh, R line, okay, or the R coordinate line, okay, and the angle made with the X axis by this particular line will be considered as a phi, okay, will be considered as a phi. Okay, getting everyone? Please let me know in the chat box whether you understood or not the cylindrical coordinate system. Is there any doubt, any question? Draw this, everyone. Over. Now, next, if you consider any element of a cylindrical geometry, okay, if you consider any element of a cylindrical geometry, so in that case, the volume of that cylindrical element will be written as R multiplied by d phi multiplied by dz. Okay, R multiplied by d phi multiplied by dz. Okay, where R is the radius, okay, or the distance from the center line. Phi is the angle made by line joining the center and that particular point with the x-axis, and z is the height, or we can say the distance from the base surface. Okay, distance from the base surface. Okay, so the volume of a cylindrical element will be given as R multiplied by d phi multiplied by dz. Okay, now here we don't have any kind of a derivation in our syllabus, so we will directly discuss the general heat conduction equation in a cylindrical coordinates. Okay, in a cylindrical coordinates. Now here only the coordinates will change. Remaining part will keep as it is. Okay, we have to keep as it is the remaining part. So how the coordinates are changed in a heat conduction through cylindrical system, we have to discuss over here. So we know that there are three coordinates r, phi, and z. Okay, there are three coordinates r, phi, z. So the temperature in a cylindrical coordinate system or a cylindrical geometry will be changed with respect to r, with respect to phi, and with respect to z. Okay, and for that purpose we have to write the conduction equation. Okay, and it will be written as dabba 2t divided by dabba r square plus 1 upon r dabba t divided by dabba r plus 1 upon r square multiplied by dabba 2t divided by dabba phi square plus dabba 2t divided by dabba z square, bracket complete. This is about the coordinates, plus qg divided by k. We have discussed this. Qg is nothing but heat generation per unit volume per unit time. Q suffix g, small q suffix g is the heat generation per unit volume per unit time, where this K is the thermal conductivity of cylinder material, which will be equal to rho C divided by K, where rho is the density of a material, C is the specific heat, whole divided by K is the thermal conductivity, multiply by dabba T divided by dabba small t. Dabba T is nothing but change in temperature and dabba small t is the change in time. So dabba T divided by dabba small t is nothing but change in temperature with respect to time. So that will be our general heat conduction equation. That will be our general heat conduction equation. Okay. So write down this equation. General heat conduction equation in a cylindrical coordinates. General heat conduction equation in a cylindrical coordinates. Okay. Now in the next equation, we know that rho C divided by K is nothing but 1 upon alpha. So where alpha is nothing but the thermal diffusivity of a material. Alpha is nothing but the thermal diffusivity of a material. Just in the next equation, we have replaced rho C divided by K by 1 upon alpha. Okay, 1 upon alpha. Or have you written the equations, two equations? Now, if we can say that if there is 1D heat flow, okay, if you are considering there is 1D heat flow, so in that case we have to consider only one axis, okay, or one coordinate only. Okay, so if you are considering there is one dimensional heat flow in the cylindrical coordinates, so in that case we have to consider only one coordinate system for the cylinder. Okay, so let us consider that if you discuss this equation. Now let us consider that in this particular figure, if the heat is flowing from the center line or the axis of that particular cylinder, from the axis of that particular cylinder towards the surface, okay, towards the surface, okay, from the axis of the cylinder towards the surface, if heat is flowing, so in that case we have to consider only r coordinate for the heat transfer. Okay, we have to consider only r coordinate for the heat transfer. Okay, what we are assuming for the one dimensional heat flow, the heat is flowing from the center line of the cylinder towards its surface. Okay, towards its surface. Okay, so the heat is flowing from this particular axis towards the surface of the cylinder. So in that case we have to consider that only r coordinate. We have to consider only r coordinate. Getting everyone? What we are assuming? We are assuming heat is flowing from the center line of that particular cylinder towards the surface of the cylinder, towards the surface of the cylinder. Okay, so in that case we have to consider only one coordinate, that is nothing but r. That is nothing but r. Okay, getting everyone? So that here for the one dimensional heat flow in cylinder, we have to consider, we have to remove out other two coordinates and we have to keep only r coordinate. We have to keep only r coordinate. So there will be a temperature change with respect to r only. There will not be a temperature change with respect to phi, and there will not be a temperature change with respect to z. Okay, getting everyone? So these two temperature change, that is the temperature change with respect to phi, that is dabba 2T divided by dabba phi square, and dabba 2T divided by dabba z square will become zero. Will become zero. Okay, will become zero. and the equation will remain or it will be converted as dabba 2t divided by dabba r square plus 1 upon r multiplied by dabba t divided by dabba r plus qg divided by k equal to 1 upon alpha multiplied by dabba t divided by dabba small t. Dabba t divided by dabba small t. Okay, getting everyone? Is there any question, any doubt? So write this equation. Okay, over this, how we have converted three-dimensional heat transfer into one-dimensional heat transfer, conduction heat transfer. Okay, now the next case is in case there is no heat source and heat flow is steady. Okay, in case there is no heat source present in the cylinder, okay, and the heat flow is steady one. Okay, so no heat source, that is nothing but what? Heat generation per unit volume per unit time will be 0, and the steady heat flow is nothing but what? The temperature change with respect to time will be 0. Okay, the temperature change with respect to time will be 0. So then this particular equation will be converted as, so this term Qg divided by K, if there is no heat source, that is nothing but Q suffix G is 0. Okay, so Q suffix G 0, then this term will be removed out from the equation. Okay, now if the heat flow is the steady one, if the heat flow is steady one, so that the temperature change with respect to time will become 0. The temperature change with respect to time will become 0. So the right side will become 0. The right side will become 0, and we will get this equation. And we will get this equation. And the equation will become the dabba 2t divided by dabba r square plus 1 upon r multiplied by dabba t divided by dabba small r. Okay, dabba r will be equal to 0. This equation we will get in case there is no heat source and heat flow is steady and one dimensional. Heat flow is steady, and you can write and one dimensional because we are considering one dimensional heat flow, one dimensional. Okay, getting everyone? Is there any question, any doubt? Please let me know whether you understood or not this particular equation, or shall I repeat? Is there any doubt, any question? Cylindrical coordinate system. What we have considered initially? Initially, we have considered one cylinder, okay, hollow cylinder, okay. So the hollow cylinder geometry, okay. The front view of hollow cylinder will be in this manner, and the top view we will see in this manner. Okay, in the front view, we can see the height of that particular cylinder, and in the top view we will see the circular cross section of cylinder. Okay, and we'll get the radius from the top view. Okay, two radius. Hollow cylinder having some thickness. Okay, hollow cylinder means, consider one pipe. Pipe is a hollow cylinder. Okay, so pipe is having some thickness. Okay, so it will have some thickness, and it will have internal radius and external radius. Okay, internal radius and external radius. Now then, for the understanding purpose, we have discussed how to locate any point in a cylinder, how to locate any point in a cylinder by using a cylindrical geometry, by using the cylindrical coordinate system. So cylindrical coordinate system having the coordinates of r, phi, and z. These three coordinates possessed by the cylindrical coordinate system. Now, what is the significance of three coordinates? Okay, first is nothing but r. R is nothing but what? The distance from the center axis, the point distance. Okay, point is located how much away from the center axis, that is nothing but r. Okay, z means what? Z is the height of that particular point from the base. Okay, from the base surface, height of that particular point from the base surface. Okay, then theta is, or the phi is nothing but angle made by that particular point with the x-axis. Angle made by this particular point with the x-axis. Okay, so that is nothing but theta or phi. So in this particular manner we can locate any point in a cylindrical coordinate system. Okay, then we have discussed this general diagram. Okay, so how to, by removing this particular cylinder, we have discussed this particular diagram, how to locate the A point in a cylindrical coordinate system. Okay, now then we have discussed that the general heat conduction equation in a cylindrical coordinates. So we have to consider that the three-dimensional equation, general three-dimensional equation in a cylindrical coordinate system. So in a cylindrical coordinate system, the temperature will change with respect to r, with respect to phi, and with respect to z. Okay, with respect to z. So that we have written this equation that the temperature change with respect to r, that is dabba 2t divided by dabba r square plus 1 upon r multiplied by dabba t divided by dabba r plus 1 upon r square plus multiply by dabba 2t divided by dabba phi square, that is the temperature change with respect to phi, plus dabba 2t divided by dabba z square. This is the temperature change with respect to z axis. Okay, now plus qg divided by k, that is the heat generated in the element. Okay, or heat generated in the cylinder. K is the thermal conductivity, is equal to rho c divided by k, where rho is the density of material, c is the specific heat of material, divided by k is the thermal conductivity, but multiply by dabba t divided by dabba small t. Okay, that is the temperature change with respect to time. Temperature change with respect to time. We know that k by rho c is nothing but thermal diffusivity, that is nothing but alpha. So here rho c divided by k is there, so that we have considered it as a 1 upon alpha, 1 upon alpha. Now next we have considered if there is a one-dimensional heat flow. So in that case we have considered that heat is flowing from the center axis of the cylinder towards its center, from the center axis of the cylinder towards the center, from the center axis of the cylinder towards the surface of the cylinder. Okay, so in that case we have to consider the one-dimensional heat flow. In that case we have to consider the one-dimensional heat flow. So that in that case we have to consider only one coordinate, that is nothing but r coordinate, that is nothing but r coordinate. And so that we have to eliminate the temperature change with respect to phi and temperature change with respect to z from the general heat coordinate, from the general heat conduction equation. So we will get the equation one-dimensional heat flow in the form of a r coordinate, in the form of a r coordinate. So it will be equal to dabba 2t divided by dabba r square plus 1 upon r multiplied by dabba t divided by dabba small r plus qg divided by k is equal to 1 upon alpha multiplied by dabba t divided by dabba small t. If in case of there is no heat source, if in case of there is no heat source present in the cylinder and heat flow is steady and one-dimensional. So no heat source present means what? The heat generation per unit volume per unit time, this particular term, heat generation per unit volume per unit time, will become 0. Okay, and the heat flow is the steady one, that is nothing but what? The temperature change with respect to time will become 0. So we will get the equation as dabba 2t divided by dabba r square plus 1 upon r multiplied by dabba t divided by dabba r is equal to 0. Getting everyone? Is there any question? Any doubt? Is there any question and doubt? So we'll stop here. Have you written all the points? Okay, just put up your roll numbers in the chat box. If you have any doubt, you can ask, or else you can leave your roll numbers in the chat box and you can join next meeting. In the next lecture, we will discuss about the heat conduction through hollow and composite cylinder. Okay, hollow and composite cylinder. सर मी कंटिन्यू करू का? हो, हा चालतंय, येतो. 11 ते 12 आहे का? म्हणजे शुक्रवारी 2 लेक्चर आहेत माझे. हा 2 लेक्चर. Remaining student, please leave your roll number in the chat box and leave this particular meeting as early as possible. I'm going to close the meeting. गायत्री जोशी, ओंकार पाटील, शैलेश पवार, समर्थ चव्हाण. Please leave the meeting and join other meeting. सत्तेचाळीस पोरं होती लेक्चरला.